All right, now it's time for the post-quiz information. There's this 10.3, and there's also 10.4, and then it's time for the test. Okay. It doesn't seem like that's too much time, but you know, with interim and Chinese New Year, this is going to actually be a lot of time. So you might want to come back and watch this video again later, right after the Chinese New Year break, or during it, actually. Anyway, on with it. Arcs and chords. We've talked about arcs and chords before, so I mean, you know what an arc is, you know what a chord is. An arc is this little curly thing from F to G, and the chord is the straight line thing from F to G. Now we're going to talk more about how they're related, or more, well, like in this picture, more than one in one circle. Two minor arcs are congruent, so this arc FG is congruent to arc JH, if and only if, and it's a biconditional, if their corresponding segments inside them, or their chords, are congruent. This is actually a mistake. I don't know what happened there. Let me get rid of this here. This little line isn't supposed to be here. That doesn't make any sense. Get rid of that. That was printed wrong in the book, I guess. These two chords are congruent if and only if their arcs are congruent, and vice versa. Okay. That is not a big deal yet. That's helpful in some of these problems that you're going to see on the test where, see if I can do this quickly, where you have some circle and you had stuff like this going on, and you knew, like, maybe there's a diameter there somewhere, and you had, you know, you maybe knew that arc, and you knew that arc, and you're looking for this one. I'm like, oh yeah, that's 180, so I can subtract from 180. And then somewhere along there, you know that there's a chord over here, and maybe a chord over here, and they tell you those are congruent. Oh, then I know that arc and that arc are congruent also. So those will help you get around. Those might be like one little kind of, almost a hidden fact that you're supposed to catch in there. So this one can sneak up on you, is all I'm saying. Remember this. Oh yeah, those chords are congruent. That means those arcs have the same, well, they're congruent, so they have the same measure and the same length, but the measure will be the one where it's going to get you. Okay. If a line or segment array divides an arc or a chord, it does so very predictably, if it's perpendicular. If a diameter or radius goes through a chord and it's such that it's perpendicular, then we know it bisects the chord and it bisects the arc. So if this happens to be perpendicular, the implications are that, well, those are congruent and those are congruent, just because of this perpendicular. And it's a biconditional. The perpendicular bisector for chord is the diameter of the circle. So if you know you've got you draw a chord, you know you've got the perpendicular bisector, you know it's going to go through the center. Let me draw that kind of straightforward this way. So say we had some random chord. If I constructed, you know, we did this with constructions a lot. If I found the midpoint and I made this line that was perpendicular going right through there, I know that line has to contain the center of the circle. That's useful if, I don't know if we do this in the problems in the book or not, new book this year, but say you were given a printed circle, or you had a circle somehow, and you knew you were trying to find where the center is. A good trick for that is, well, you pick a chord, construct the perpendicular bisector, or locate or measure or whatever the perpendicular bisector to that one. You know the center has to be on that line. Do that somewhere else. Find the perpendicular bisector of this chord. You know those will have to intersect at the center. Sorry, trying to mark my perpendicular bisector is not working very well, and it's really tiny. Okay, that will have to be the center. So if you just have a random circle without a center marked, it can be found that way. Okay. Theorem 10.5, in the same circle or congruent circles, two chords are congruent if and only if they are equidistant from the center. Okay. This one, I'm going to redo this down here. This one's saying if, again, it's a biconditional. It's about FG, the segment, being congruent to JH, the segment. That goes hand in hand with the fact that LX is congruent to LY. So the same distance from the center means this. That's why I was going to go down here. You're talking about this chord, and we're talking about equidistant from the center. Like, what does that mean? This chord has a distance from the center. We talked about, it's been a long time, but we've talked about the distance. How do you find the distance between a line and a point? It's defined as the perpendicular distance from that line to that point. So when we talk about the distance from the, because there'll be problems, like word problems that just say, this chord is 3 inches from the center. Like, well, what does that mean? It means if you were to draw this perpendicular right here, that would be 3. That is the distance from a chord to the center. It's this thing right here. Okay. And if two chords are congruent, you can kind of push them out from the center into the circle, and they'll kind of get stuck on the circle at the same distance from the center. And vice versa. If you know you have congruent chords, you know they're going to be congruent distance from the center. If you have these kind of things, you know, are congruent, like these partial radii, and they stop at the same length when they hit their chords, you know those chords are congruent. If the chords are congruent, the arcs are congruent. Okay, this is kind of a forwards way to talk about all this. Draw a circle with center O, radius, put my drawing tools on, radius 12, and a chord 6 centimeters from O. Okay, so I need to draw a circle radius 12. Well, I guess I should probably get a ruler out for that, but that's a little hard on this. I would draw a radius of 12. I would take my compass and I would draw a circle around that. Oh, can I do that quickly on this thing? I don't think I can. I think I'm going to have to fake it. Oh wait, I could get a compass. Ah ha ha ha. Forgot about the compass. This will be perfect with the compass. All right. So I could draw. You don't need to do this with the compass. I just need to make a circle. You could. Well, actually, a compass is probably the best way to do it. So there's a circle of radius 12, and a chord 6 centimeters from O. Oh yeah, it's called circle O. So this is point O. Draw a chord 6 centimeters from that. Well, that's kind of tricky. Well, one way to draw something 6 centimeters from that, I could, let's get this out of the way. I could measure 6 centimeters along here, which would kind of look like the midpoint. Measure that out so it's 6 centimeters, and I could draw this perpendicular because I know I want this to be the distance from this point to this line. So this length, the distance, the 6 I'm calling the distance, must be perpendicular to that. All right, so I'm going to cheat. I'm going to use this segment tool. You would have a ruler and life would be a little easier, but I have to make this so that I'm sure that it's perpendicular. This doesn't look perfect, but it's not bad. And if that's really 6 and that's really perpendicular, I've drawn the correct length chord. Now the question is, how long is that? If we know this is 6 and we know this is really perpendicular, so even if it's not, let's pretend it is. The question is, well, how long is the chord? How long is it from point A to point B? I'm going to do it this way. I know this is perpendicular. I know this is 6. I know how far it is from O to A. How far is it from O to A? Oh, wait, that's how far it is from O to A. That's the radius of the circle. So I've just located a right triangle here, and I've got two sides of a right triangle. Life is good. I know if this is 6 and this is 12, well, there's a trick that tells me this is 6 times the square root of 3. I could have also found that with Pythagorean theorem, but I know if this is 6 and it's half the hypotenuse, then this side has to be the short leg times the square root of 3, and this is going to be 60-degree angle, blah, blah, blah. This is the same. Remember, I just found out that this point here, C, is the midpoint of AB because this is perpendicular. There was that theorem we just did. If the radius is perpendicular to the chord, it has to be the bisector. So there we go. This whole thing is going to have to be 12 times the square root of 3. Lovely. Anyway, that's a common trick to have to build these right triangles. And the part people forget about those is this. This thing right here is not hard to find. It's the radius of the circle. Don't forget you can add in a radius whenever you want. You know the length of it if you know the radius of the circle. Radiuses go everywhere we want them. So if I wanted to connect O to this point over here, I know I have to have a length of 6. That's very helpful. I don't think I need this for a while. Okay. Find X and Y. All right, so the radius of the circle is 6. That's great. So if I want to know the distance from O straight up here to the top, guess what? It's 6. And that kind of thing. I know this, whatever this is, Y over here, it's the same thing over here. This has to be a bisector because it's perpendicular. Oh, but I have another 30, 60, 90. This is 60, this is 90, this must be 30 from last chapter. If this is the hypotenuse, the side opposite the 30 is the short leg. It's kind of hard to tell on this picture, but that's half the hypotenuse, and this is 3 times the square root of 3. This is also 3 times the square root of 3. So Y is 3 times the square root of 3. What's X? Well, we just said from O to the top here, that's a radius, so that has to be 6. So since this whole length, whatever here, that whole length has to be 6, this part has to be 3. All right, find the following arc measures. All right, here's where those things will sneak up on you. Whatever I find for this arc measure DH, the arc CD is going to be the same because these chords are congruent. All right, what's GH? Oh, here's a chord. Oh, did they tell me this is a bisector? I don't think they did. I think they kind of have to draw this in. We would have to know that, or we'd have to know those are congruent or something. This is only an interesting problem if we know that's congruent. Or sorry, if we know this is a perpendicular bisector. So go ahead and draw that in. Let's assume that. That makes that 44, and that's our first one. Okay. Then I know these two have to add up to the rest to make 180. From C to G is 180. excuse me, and this part's 44, so C to H, that's going to have to be 136, is that right? To make 180 all the way around from C to G. And then these are the same. Those two are the same. So they both have to be 136 divided by 2, which is 68. Is that right? C to G is 68. 120, yeah. And then AC is from here to here. Oh, that's the same. I already did that sort of. It's 136. It's the rest of the 180 over there. So there were some tricks we used from this section to help us get around that, and it was kind of hard to see. What I keep telling people in this chapter, which I think is helpful, and it's something I've noticed, is that when people are looking to find, like, well, how am I going to figure out the measure of this? Usually the answer to finding out something in this part of the diagram is found in completely another part of the diagram. Like, to find this, I had to look at this 44 up here and work my way back to it. Or sometimes the answer is, oh yeah, it's this. I know it's perfectly equal to something over in a completely different corner. So don't forget to back up from these pictures and kind of zoom out with your eyes and look around the whole thing and go, you know, I'm looking for an answer in the lower left, but the answer might be up in the upper right. Okay, that's kind of vague advice, but it's amazing to me how often that turns out to be the case. All right, find B to D. Well, if this is 6, this is 6. If those are congruent, well, then I know things like BD and GF are congruent. Oh yeah, so if that's 5, this has to be 5 because H is the midpoint there, and these are congruent. There's another midpoint. These have to be 5. Like, all this stuff is congruent. It's really predictable, actually. What am I looking for here? I'm actually looking for the measure of the arc BD. Okay then. Well, that's a degree measure. I don't know any degrees in this picture yet at all, and I'm really looking for the angle size that, I mean, if all else fails, what we really want here is the central angle BOD. I need to know that whole angle. Well, that I know is cut in half by this angle bisector OI, and I can find this angle here, or either one of them, because I'm in a right triangle, and I'm in a right triangle that has legs of 6 and 5. So I can use what I know about trig. I can say the tangent of, well, I'm going to call this x, this little angle right here. The tangent of x degrees is opposite over adjacent. Calculator time, because what I need to do is find the inverse tangent of 5, 6. Remember that? And that is 39.81 degrees. I'll put that back on here. Okay. And that's it. Okay, I will see you in class.